harmonic and the motion and the wave. So when the spring compress or elongate, so that it will store the energy. So spring here, so this is the initial layer is air, so we extend it to delta L. So in this case, the K is a spring constant and is a mass. So angular velocity can be calculated omega is equal to square root of K by M. So it's a K is a spring constant, M is a mass. The frequency also can calculate it if it's a omega by 2 pi. Period T is a 1 by M. So this is for the spring calculation. With this problem, the blouse whose mass M is a 380 gram is fastened to a spring whose spring constant it is a 35 Newton per meter. The blouse is a pulled in the distance h 11 centimeter from its equilibrium position at the h equal to 0 on the frictionless surface and released from the rest at the t equal to 0. A. What are the angular frequency, the frequency and the period of the resultant motion? B. What is the amplitude of the oscillation? C. What is the maximum speed Vn of the oscillating blouse? And where is the blouse when it has this period? D. What is the magnitude of the acceleration? E. What is the phase constant phi for this motion? F. What is the displacement function? So the first thing we have to calculate is omega here. So this is the angular frequency. Angular frequency equation is square root of K by N. In this case, there's a K, the spring constant. The spring constant is given. Spring constant is a 35 Newton per meter, so you substitute here. And then the spring is a mass, 380 gram. 380 divided by change to the kilogram, divided by 1000, so that's 0.38. So you got this 9.176 radian per second. So this is for the omega. And then this based on the omega that we have to utilize as our frequency. The frequency F is equal to omega by 2 pi. So then 9.76 divided by 2 into 3.1410, you got the 1 by 6 hertz. And also there's a die. Die is equal to 1 by frequency, 1 divided by 1 by 6, so that's 0.64 second or 340 millisecond. And the B, what is the amplitude of oscillation? So Hm is 11 cm because here is given. The block is put at the distance is 11 cm. So amplitude is the maximum, the distance is elongation at 11 cm. C, what is the maximum speed Vn of the oscillating block? Where is the block when it has this period? So the Vm can be calculated omega into Hm. So Hm is 11 centimeter, so change to the meter divided by 100. Omega we already know is 9.76. So we substitute you got the 1 by 1 meter per second. And D, what is the magnitude of the acceleration? Acceleration magnitude is the Am is the omega square into Hm. So omega we already know is 9.76 square, and the Hm is 11 centimeter divided by meter, so divided by 100. You got the 11 meter per second square. And E, so what is the phase constant phi for the motion? So the H is equal to T equal to 0. In this case, phi is equal to H and Hn. Cos phi H by Hn. So this is the 1 by 1. So you got a 0 degree. F. What is the displacement function? Displacement function H is Hm cos omega t minus plus phi. So in this case, H is Hm already know. This is for the 11 centimeter. So 0.11 meter. And cos omega A we already know that 9.78, and the angle phi is angle 0. So we got the HD 0.11 cos 9.78 t. So this is for the that equation to calculation. And also another problem. At the t equal to 0, the displacement h0 of the block is at minus 8.5 centimeter. The block velocity v0 is at 0.92 meter per second, and its acceleration a0 is at 47 meter per second square. A, what is the angular velocity of the system? B, what are the phase constant phi and the amplitude Hm? So firstly we calculate. So we write down the equation a0 is equal to Hm cos phi. This is equation 1. V0 is a minus omega Hm psi phi is equation 2. A0 is a minus omega squared Hm cos phi. This is the equation 3. So in this case, there's equation 1 is divided by 3, A0 by A0. So Hm cos phi by minus omega squared Hm cos phi. So in this case, we can calculate omega squared is square root is minus A0 by A0. So therefore, the omega is the square root of A0 by A0. So A0 is the initial acceleration. Initial acceleration already given as 47 meter per second square, and A0 is minus 8.5 centimeter. This is for this is the negative elongation. So this is the compression. So this is the minus 47 by minus 8.5. So you got the 20. So square root. So you got the 23.5 radian per second. And then equation 2 is divided by 1. Equation 2 is here, and equation 1 divided by here. So V0 by A0 is equal to minus omega Hn sin phi divided by Hn cos phi. So this Hn are cancel. Sin phi by cos phi is tan phi minus omega tan phi. So tangent phi is equal to minus V0 by omega A0. So the minus initial velocity V0 is already given as minus 0.92 meter per second, and initials are elongation A0 is minus 8.5 centimeter. So we substitute. So you got a minus 0.401. So phi is equal to tangent inverse minus 0.401. So you got the minus 25 or 155 degree. And therefore the Hn is A0 by cos phi. So phi is a minus 25. So then we substitute this equation. Minus 0.085 divided by cos minus 25. So you got the minus 0.94 meter. And phi 1.5. Hn is equal to 0.085 divided by cos 1/5. So you got the 0.094 or 9/4 centimeter. So this is for the springs calculation. So that when the springs are compressed, there is also the retain the energy. The energy is simple harmonic motion. So energy is a UT is equal to half into Ka square. Is equal to half into Khm square cos square omega d plus phi. And that simple harmonic motion equation is a mdh square by dt square plus bdh by dt plus kh is equal to 0. In this case, hd is equal to hm e power minus bd by 2m cos omega dash d plus phi. So this is the omega dash is the oscillation frequency, can be calculated square root of k by n minus b square by 4m square. So this is spring. This is mass. So oscillation can be calculated. Oscillation is the hm e power minus bd by 2m. This is the Hn e power minus bd by 2m. So EDS is our energy function half into Khm square e power bd by minus bd by m. So this is for the energy function of a spring. Spring got the simple harmonic motion. So this is the energy function of a simple harmonic motion.